Hi, I'm Sarah Noble.
And I'm Roman Bradford, and this is our video for the Transistor Gain lab.
So this is a transistor, and a transistor is a semiconductor with a solid and non-moving part to pass a charge. It has 3 or more terminals used to connect to an external circuit. On the right with the flat base facing you is the emitter. In the middle we have our base, and on the left we have a collector. The 2 major functions of a transistor is it works as an amplifier and a switch. When a transistor works as an amplifier, it takes a tiny current at one end, or an input current, and it produces a much larger current, an output current, and it kind of works like a current booster. And a really good example is hearing aids. So when a transistor runs as a switch, it's going to always have a small current running through it, but when we open that switch up, it'll cause an even larger current to flow through another part of the transistor. So essentially that small current is allowing for the larger current. When the switch is open, if it's off, you'll always just get a small current. A really good example of this is computer chips.
We use a digital multimeter to test the gains on our transistor. Our transistor has a gains of 220. The gains are the ratio between the current coming out of the emitter and the current going into the base, which means that the current coming out of the emitter is 220 times what's going into the base. The gains of the transistor can vary based on temperature. So if I grab it, it rises, and if I let it go, eventually it'll cool down and drop. So here is our circuit. We've got a 100 ohm resistor in series with our variable power supply, and a 100 ohm resistor coming out of our transistor. We're measuring the gains. When the variable power supply is at 6 volts, we're measuring 53.7 coming out of the resistor or transistor, 0.17 going in. That's a gain of about 300. If we bring the voltage down to 3 volts, we see 0.07 milliamps going into the transistor and 23.8 coming out. That's roughly 300, a gain of 350. And if we go all the way down to 1, we see 0.02 milliamps going in, 4.9 coming out. That's a gain of about 250. So we recreated our circuit in LT Spice. When we measured the current coming out of the base, or coming out of the emitter, we got 52.26 milliamps, and the current going into the base was 291 microamps. So that ended up being a gain of 179.
Next, we tried changing the voltage to 3. We got the current coming out of the emitter to equal 22.58, and then out of the base we got 112.38. If we divide them, we get a gain of about 200. Finally, we changed the voltage to 1, and we got a current running through the emitter to be equal to 3.164 milliamps, and then through our voltage source we got a current of negative 14.58 microamps, and it's negative because that's which way the current is going. When we divide them, we get a gain of about 216. Finally, let's look at the DC gain on our data sheet. We're expecting that the gain would be a minimum between 35 to 100. So the biggest takeaway we had from lab was, why was our LT Spice's gains so much larger than our actual circuit gains? And we learned that transistors, you can't ever expect it to have a specific amount of gain. You know from the data sheet that you're going to get a gain of at least 35, probably closer to 100 for our specific transistor, which was a PN2222. So getting values all the way from 100 to 300 was very normal.